Okay, so good afternoon. Just kind of a side note, I started to develop a bit of a sore throat during the first my first class today, so I'm hoping I'll be able to get through this one without too much trouble, but might end up having to cut it a little bit short if my voice doesn't quite last. But the um the plan for today is to cover the substitution rule, the first of a series of integration techniques that you'll see between the end of this course and Calc 2. But a couple administrative notes first. Um, all the remaining homework is posted, so you have access to essentially all the remaining work for the course, so you can plan ahead. Um, just don't forget about the final exam that's during final exam week, which is listed below. And usually in the last couple weeks of class, I like to start each class with just a summary of what the next, what the rest of the course is going to look like, so that we are kind of reminded what happens when and can plan ahead. So the plan for this week is finish up chapter 5, substitution rule, and introduce chapter 6 with 6-1 area between curves. Then, of course, we have Thanksgiving break next week, so no class. Coming back, we have volumes on Monday and then integration by parts, chapter 7 on Wednesday. So we're kind of hitting a couple of topics in chapter 6, hitting one topic in chapter 7. So uh, a couple of assorted topics. We're certainly not covering all of chapter 6 and 7. And then we'll leave Monday, unless something changes, we'll plan to leave Monday as kind of a reading day, review of the sample final exam, prep for exam, anything like that. So I don't want to go much past, I don't want to go any further than 7.1. I think at that point we might as well just start calling it Calc 2. But I think 7.1 ties in with 5.5 well enough, and then same with 6.1 versus 6.2. So 5.5 and 6.1 are kind of still firmly in the realm of what we're calling Calc 1 these days anyway. And 6.2 and 7.1 we'll see are kind of related to those two ideas. If we start going too much further, it's like you're not going to really get very much out of it, being the end of the semester. So that'll be the plan for the next 2 weeks. And then final exam week, um, I'll open up the final on Friday the 6th. So it's actually a few days before final exam week, but that way you have the weekend if the weekend works better for you. Or you can take it a little earlier if you have a bunch of stuff due final exam week, you can get some work out of the way that way. It is comprehensive. It's chapters 2 through 5 in section 6.1. And there will be a 6-point bonus problem from section 7.1 on integration by parts. So I'll post more about the final exam when we come back from break. But the sample final, it should already be up as well. So you should see the sample final exam on there. So if you want to start looking at that material, reviewing the material over Thanksgiving break, you're certainly welcome to do that. Okay, the two quotes of the day today, well, one of them we certainly discussed before, and one of them touches on an idea that we've discussed before. The first quote from my favorite professor, Bill Layton: good decisions come with experience, and experience comes from making bad decisions. So, we're near the end of the semester now. It's kind of crunch time with projects and papers and final exams and things coming up pretty soon here. Look back over the semester and ask yourself, is there anything this semester that didn't really go the way that you wanted? Is there anything you weren't really happy with at the time? Maybe it was preparation for a past exam or scrambling at the last minute to get a project in. If you have a bad experience that came from making not so great a decision earlier in the semester, looking forward to crunch time, what can you do to mitigate that, right? What can you do to learn from that experience and make a slightly better decision next time? And this quote on margin: you must create more margin so you have room for what's important, not merely urgent. And to that end, I would say, Thanksgiving break, having a break is great, but especially for a 2-day week course, taking a whole week off kind of means that we're essentially taking a week and a half off. And I would be cautious about doing something like, say, stepping completely away from the material and not touching it from Wednesday the 20th until Monday the 2nd, because the turnaround is really quick, especially this year. Thanksgiving break or Thanksgiving is the last possible day that it can be. And so the Thanksgiving break is very late this year. That means we only have 1 week when we come back from Thanksgiving break, and then we're turning around and it's final exam week already. And actually, our final exam even opens up the same week that we come back from Thanksgiving break if you choose to take it a bit early. So just be really aware of that. You know, a lot of times we come back from Thanksgiving break and there's 2 weeks and then finals. We really didn't have 1 week and then finals, super quick turnaround. I would strongly recommend, you know, Thanksgiving break, like definitely take some time off, relax a little bit, but maybe Monday or Tuesday, you know, go through your courses, make some plans for what you want to do that next couple weeks. Maybe go through, knock out a homework set here or there, or do a little bit of review or something like that. Maybe do the same thing on, say, Saturday after Thanksgiving. You know, take a bit of a break, but don't step completely away from the material, because kind of getting that momentum back up in just a week is pretty tough to do. So leave yourself some margin, right? Put in a little bit of work over Thanksgiving break, build a little bit of margin for that crunch time, finish strong, and then when you hit, you know, Friday the 13th or whatever, when you have all of your projects and papers and finals all in, you know, then go and party, you know, then do whatever you want for the next month. You're good to go then. But, you know, make it a little bit more like a working vacation for Thanksgiving break, I would recommend. And then, you know, you just got a couple more weeks, and then you're kind of home free. All right. So any questions, thoughts, anything on the last couple weeks of class? Okay. So moving on then to the substitution rule. Okay, so the substitution rule is the first of our real integration techniques, but something that we don't want to get to kind of forget about or get distracted away from is what we've already done, right? I mean, we've already solved lots of integrals without using these, you know, something like formal integration techniques. So if we're looking to find an antiderivative or to solve an indefinite or definite integral, the first thing we look at is, do I just know what the antiderivative is? Essentially a direct table lookup. F of x equals 2x. I know that x squared differentiates to that. The second is, you know, kind of pretty similar to one. There are some problems you can look at that seem quite different from step one, and some that seem quite similar. But for instance, so the second step is kind of look up in a table, use kind of an educated guess, a gut feeling, make a guess at what you think the antiderivative is, and then fix it, right? So if little f equals x, I say, I mean, I kind of think that quadratics differentiate to linears, so maybe big F equals x squared. Does that work? Not quite, but we're just off by a constant multiple. We can fix that. And then any kind of algebraic simplification as well. Something like little f equals x cubed plus x to the sixth over x squared. We can simplify that to little f equals x plus x to the fourth and go from there. Or we can take, you know, the antiderivative of the sum is the sum of the antiderivatives. We can make algebraic simplifications like this to help us get to our antiderivative. This also happens with logs inside of integral signs. If we're integrating log of stuff, a lot of times we'll see something like this pop up where there might be a simplification we can make first. So it's important when we're solving integrals in the substitution rule section or integration by parts section, or more generally, that we don't forget the quote kind of simple things, right? It's easy to jump right to a more complicated rule and say, wait, can I apply this like big sledgehammer? Well, sometimes all the problem needs is a little tack hammer. So don't forget what we've learned already, but we've already seen that there are some instances where, well, we come up to an integral that doesn't really yield to these simpler techniques. And that's where the discussion of integration techniques comes in. And we'll be talking about the substitution rule, which is kind of, in a sense, the inverse of the chain rule. And we'll be talking about integration by parts, which is kind of, in a sense, the inverse of the product rule. And others will be introduced in Calc 2 as well. So Calc 2 will pick up with these integration techniques and some others. Somewhat like, I don't know, interestingly or ironically, the chain rule for differentiation is a lot harder, is a lot more challenging for folks than the product rule. But kind of in the inverse world, the opposite is true, which is often the case when we look at inverse problems. The substitution rule, I think, is more straightforward for most folks. And integration by parts, I think, is a little more complicated for a lot of folks. The main challenge in substitution rule is kind of the same as the main challenge in the chain rule, deciding how you want to decompose your function. Okay, so those are the two main additional integration techniques we're going to look at in this course, and then, like I said, picking up with others in Calc 2. So what is the substitution rule? Well, theorem substitution rule. If u equals g of x is differentiable with range I, so range I, so the outputs of g are in I, and if f is continuous on that range, so if f is continuous on the inputs into f being the outputs from g, then we want to, if we want to integrate f of g of x times g prime of x dx, we can rewrite that as integral f of u du. Now you might look at this and say, this seems like a very strange integrand. I mean, when are we ever going to want to integrate f of g of x times g prime of x dx? Well, it actually turns out maybe a little more often than you might think. So let's take a look at some examples. Okay, let's look at integral x plus 1 to the 10th dx. So here I recognize that this is a 10th degree polynomial. It's nice and continuous everywhere. It's nice and differentiable everywhere. I don't have to really worry about anything about the behavior of this function. But I do have a little bit of an issue, right? I know that it would be really nice if this was just integral of x to the 10th dx. That would be like x to the 11th over 11 plus c. But we have this annoying x plus 1 to the 10th. So what could I do? This might actually be close enough to one of these, direct table lookups that I might be able to make an educated guess and get the right thing. And so this is an easier substitution rule problem. You probably could make an educated guess and end up with the right answer. But if I wanted to use substitution rule here, just to introduce the idea, what am I looking for? Well, I'm looking to break my function up into the composition of two functions. Right, the big thing going on here is this f of g. So I want to decide what is g of x and what is f of t. So, I mean, I guess I could pick g of x to be like x plus 1 to the 10th. And then, well, that would leave f of t as just t. But that doesn't seem like it's really going to help very much. Why is that? Well, I mean, this would be really nice, just integrating u du. F of u would just be u then. But the problem is that g prime of x is 10x plus 1 to the 9th. I don't see a g prime of x anywhere in here, right? I can't write this integrand as f of g, which would be x plus 1 to the 10th, times 10 times x plus 1 to the 9th. Like, it doesn't quite work out. So if I put too much into g, it doesn't quite work out, just like in the chain rule. If I get too greedy, so to speak, doesn't work out. Oh, OneNote only allows you to undo so many things. There we go. On the other hand, if I pick something way too small for g, I don't actually get anywhere. if f of t is t plus 1 to the 10th and g of x is x, well, f of g of x is my integrand that I have up here. G prime of x is 1. That works nicely. I could, in theory, do this, but then I'm just integrating u plus 1 to the 10th. I don't actually get anywhere, right? So if I'm too greedy, if I put too much into g, it doesn't work. If I put too little into g, it doesn't work. There's kind of like a Goldilocks function to put into g. And really what I often look at is I say, well, what's kind of the overall structure of the function, like stuff to the 10th? Can I integrate stuff to the 10th? Can I integrate like t to the 10th with respect to t? Sure, I can. So can I make f of t something like t to the 10th? And then what do I need to plug into here to get x plus 1 to the 10th? G of x would be x plus 1. This kind of splits the complexity nicely between g and f. And g prime of x would just be 1. So I see that this integral is indeed integral f of g of x. That's x plus 1 to the 10th times g prime of x, which is just 1 dx. Now, typically, the way that I would write this is I would write this as something like u equals x plus 1, and then du equals 1 dx. Remember differentials from a couple of chapters ago? We think of this as a differential. So du equals u prime of x dx. And my integral then is going to equal integral f of u du. Or that's going to be integral u to the 10th du. Well, this is 1/11th u to the 11. That's not like a u double prime, that's u to the 11th power plus c. And now one little detail, I introduced this variable u. The original question was phrased in terms of the variable x. I should substitute back in to write my answer in terms of x. U is x plus 1. And there's my answer. So this was a little more convoluted than we would typically see in a substitution rule because I kind of walked you through the process of like getting a wrong g this direction or that direction, putting too much into g or too little into g. But your first couple of times doing a substitution rule problem on your own, you are likely to fall into that. You're likely to pick the wrong thing, pick the wrong way to split up f and g, and go down one route and say, okay, wait, that doesn't quite work. Let me back up a little bit, try something different, right? Takes a little bit of trial and error um, until you get enough experience with this to be able to split up your overall function into its component functions in a way that works nicely. And even if you have a lot of experience for more challenging problems, a lot of times it does just take a couple of different tries. Okay, let's look at this example. Integral of 2x times square root of x squared plus 3 dx. Now this one I notice, the thing that kind of makes things difficult is the square root, right? If this was the square root of something simpler, say if this was just square root of x squared, then I'd effectively just have 2x times x, right? It would be pretty easy to work with. Maybe there's an absolute value of x there that makes things a little more complicated, but I could work around that pretty easily. So the thing that makes this challenging is the fact that I have a square root of x squared plus 3. I would really like to do something like u equals x squared. Well, if I'm going to be greedy and use x squared, why not try to just do the whole inside of the square root? I can probably go as far as x squared plus 3. That makes my square root even simpler. And then what is u prime, or what is du? So du is going to be u prime of x, 2x, dx. So practically speaking, when I'm looking at solving these substitution problems, I guess a u, make an educated guess for a u, like x squared plus 3 here. I figure out what du would have to be. And then do I see something that looks like du in my integral? I do. So in other words, this is going to be the integral of square root of x squared plus 3, and then, 2x dx. This is what's going to turn into du. And this is going to turn into square root of u. So strategizing ahead a couple moves. One, I see that if I pick u equals x squared plus 3, my du is going to be 2x dx. And I do see that popping up in my integral. And two, I see that the resulting integral is going to look like integral of square root of u du. Can I do that integral? Yeah, I can. That's just a power function. So I need to be good at figuring out what simple integrals I'm able to do and which ones I'm not able to do. And I need to be good at doing the derivatives, doing this step, so that I can see whether that du also pops up in my integral. But I see with this substitution, I get integral root u du. Well, root u is just u to the 1/2 power, so that's u to the 3/2 power, divided by 3/2 or 2/3, plus c. Oh, and I've got my answer in terms of u. I should switch it back into x. So 2/3 times x squared plus 3 to the 3/2 power plus c. Any questions on that one? I don't know why that numerator x is in a funky font, but there we go. Okay, so next example, integral of 1 plus x over 1 plus x squared dx. So if I look at this one, I might think of a couple of different possibilities here. If my denominator was simpler, say like just x squared, if I got rid of the 1 plus, I might be able to make some cancellation, make things a little simpler that way. If my numerator was simpler, if I got rid of the 1 plus up here, that might help also. What if I pick, like, say, u equals 1 plus x squared? Well, then du is going to be like 2x dx. Du basically looks like x dx. We know the constant factors we can often fix pretty easily. But du does not look like 1 plus x dx, unfortunately. If I pick u to, say, just be x squared, I get the same du. If I pick u to be 1 plus x, then my du is just dx. That doesn't really do a whole lot. I have this whole denominator that I don't know what to do with. So what can I do here? Well, it seems the substitution rule is complicated to apply here. It doesn't seem like it's applying nicely to this integral. Can I go back up here and say, is there anything else simpler that I can do before I jump to substitution rule? Do I just know that this function is the derivative of something? Do I just recognize it? Not really. Can I make an educated guess? I don't really think so. I think this would be a really tough one to make an educated guess for. Can I do any algebraic simplification? Well, actually, I can break this fraction into two fractions, right? And remember, the integral of the sum is the sum of the integrals. Well, nicely enough, I know exactly what the first one is. I recognize this. I know whose derivative is 1 over 1 plus x squared. That's just arctan x. Oh, the second one, I'm not so sure about this one. But I did get a bit of a hint before when I was trying just playing around with my substitution rule at the beginning of this problem. It didn't quite work out, but I do remember that if I had u equals 1 plus x squared, that whole denominator, that meant du was 2x dx. I almost have a du here. I have an x dx, not a 2x dx. Well, surely I could put in a 2, a factor of 2, and take it out, right? I could just multiply by 2 halves inside the integral, for instance, leave one of the numerator 2 in there and pull the 1 half outside of the integral. So this is 1 half integral. This 1 over 1 plus x squared is going to be a 1 over u, and the 2x dx makes a du. Now, one thing that I have to be really careful about with with really all of these integration techniques, one thing I have to be really careful about is what I sometimes call the bookkeeping or the accounting. I need to make sure that I have used everything in my original integral. I didn't like skip over a factor of x that's still there that I didn't use or leave out something. And I need to make sure that I didn't use anything that's not there. That I didn't, I need to make sure that I wasn't, say, looking at this integral and saying, oh yeah, this u substitution works, but meanwhile I'm missing an x, right, for my du. So I have my 2x dx. I've used that to make du, and I have my 1 over 1 plus x squared. I've used that in the 1 over u. So I've used everything in my integral and nothing that's not in my integral. So all the bookkeeping, all of the accounting works out, everything balances out. This gives me arctan x from before plus 1 half. An integral of 1 over u is log absolute u. We'll throw a plus c on for good measure. And then just like before, I should reframe my answer in terms of the original variable. So arctan x plus 1 half log of 1 plus x squared plus c. I can get rid of the absolute values because I see that 1 plus x squared is always positive. So I used a bit of algebraic simplification. Maybe that's where I should have started ideally, but I just wanted to show that, trying to apply substitution method to this kind of like almost worked, but not quite. But with a little algebraic simplification, breaking off that 1 over 1 plus x squared and making that integral arctan x, that left us with integral of x over 1 plus x squared, which we could use substitution method or substitution rule for that solution. Okay, so what about something like 1 over ax plus b, the integral of that? Well, here I'd really like to do something like u equals ax plus b, so that I'm just integrating something like 1 over u du. That looked like kind of what I did above, a little bit. Then du would be a dx. Now I don't see an a dx in my integral, but I do see a 1 dx, and I know that I can fix constant multiples pretty easily. Sometimes what people do, I don't recommend this at the beginning. After you get pretty good with substitution rule, it's not a big deal to do this. But sometimes what people will do is they'll flip this around and say dx equals 1 over a du. and then they'll just swap 1 over a du in for dx. This is kind of an okay thing to do, but I don't recommend doing it initially. I wouldn't recommend doing it until maybe Calc 2 when you're dealing with more challenging integrals and substitution rule. And the reason is that it's easy to convince yourself that something works when it doesn't. So where was an example from up here? Like this one, for instance, if I had chosen g of x equals x plus 1 to the 10th, then g prime of x is, or sorry, g is that which we will now call u, and then du was 10x plus 1 to the 9th dx. Well, if I try to divide through by this, if like dx is 1 over 10x plus 1 to the 9th du, I mean, it might feel like I could always make any substitution work, but the problem is now I've got an integral that has like, I'm trying to integrate, what would it even be? Like, I guess u, like integral of u over 10x plus 1 to the 9th du. So now I have like an integral with some u's in it and some x's in it. And it's really easy to mishandle something like this because u and x are related to one another. It's really easy to like accidentally pull an x out or something like that. Or so I wouldn't recommend doing this. The way that I would recommend fixing the integral, like I want to do something like this. The way that I would recommend getting an integral into a format where I can do this substitution is by just using integral properties. So I know that I want an a dx. So I know I can make this a over ax plus b dx. I multiplied by a inside the integral. I can divide by a inside the integral and then bring a 1 over a, that factor outside the integral. Right. So I can manipulate my integral itself to get it into a form where my substitution just readily applies, rather than trying to manipulate the pieces of the substitution to get it into a form that looks like what's in the integral originally. I think it's much more, much easier to make a mistake manipulating the pieces of the substitution rule than it is manipulating the integral itself. But I do see my ax, or my adx here on top, and my ax plus b down here. So this gives me 1 over a integral. 1 over ax plus b is 1 over u. A dx is du. I know that I've used everything in my previous integral, nothing that's not in that integral. This is 1 over a log absolute u plus c. Or this is 1 over a log of the absolute value of ax plus b plus c. Okay. Any questions on any of this? Okay, let's look at this example, this integral. I have integral of x over 1 plus x to the 4th dx. Now, what I would probably like to do is make u equal 1 plus x to the 4th. That's kind of like, that's the greedy u, something like that, right? Just put everything in the denominator into u, and then I have like integral 1 over u. Does du work? Du is going to be like x cubed dx. And I have an x to the first power dx. Can I do anything to make an x to the first power look like an x cubed? Not really, right? I would not want to do something like, multiply top and bottom by x squared, and then pull the 1 over x squared out of the integral. That's not going to work. I can't just go and pull that out of the integral. That's not an allowable integral property. I can see that pretty clearly, right? So I don't think this substitution is going to work. But I do understand that this 1 plus x to the fourth in the denominator is the thing that's causing most of the problems here. I should also note, ideally we would want to check, okay, is this just the derivative of a function I know? Probably not. Is this close to the derivative of a function I know? Not really. Maybe I'd try a couple of log of something ideas, but we can pretty quickly see that's not going to work super nicely here. And I would ask, are there any algebraic simplifications I can do? And again, not really. I can't break this into multiple fractions, anything like that. Not much that I can do here as far as the simpler stuff goes. My initial look for a substitution doesn't quite work. But the overall strategy of what I'm looking for here is making the denominator a little simpler. What if I thought of my denominator as like 1 plus x squared squared? What if u was like x squared? I know u being x to the fourth or 1 plus x to the fourth isn't going to work, because that means that I need an x cubed dx for my du, and I only have an x dx. But if I consider that constraint that I only have an x dx, at least it kind of looks that way to use for du, if I let u be x squared, does that help at all? This of course gives u equals x squared gives du is 2x dx. I know I can fix constant factors, not a problem, but it's really that x dx that pops out that's super helpful. This choice for u gives me a good du, right? I can make this a 2x and a 1/2. So I have a 1/2 integral 2x dx is du. And if u is x squared, then u squared is x to the fourth. So I have 1 over 1 plus u squared. Now, I mean, at first glance, it might seem like I didn't put enough into u to get something nice enough out to integrate, except that I actually recognize this function, right? I recognize that 1 over 1 plus something squared is the derivative of arctan something. So this is 1/2 arctan u plus c. U is x squared. So we have 1/2 arctan of x squared plus c. That was kind of a complicated one. Let's actually, so my claim is that this is, say, big F of x. Let's actually differentiate the check. Big F prime of x, well, the constant, of course, differentiates off. I get 1/2. Arctan of stuff gives me 1 over 1 plus stuff squared. X squared squared is x to the fourth. Times the derivative of the stuff times 2x. The 2's go away, and yeah, so that actually does work. If I do a complicated substitution problem, sometimes maybe just to make sure that I got everything right, I got my constant factors all right. Maybe if there's a negative sign that popped up, I carried that through properly. I didn't forget anything in the integrand or something like that. If I differentiate at the end, I should get my original integrand back. And I see that that's exactly what I get here. X over 1 plus x to the fourth. Any questions so far on this one? So these first couple we did are, these couple here are maybe more straightforward. These would be like easier substitution rule problems. This one, because we had to do a little work on the front end, this would be like an easy to moderate difficulty substitution rule problem. This is probably an easier one. This is maybe in the solid moderate level. Speaking in terms of, the difficulty that would be expected in, say, the calculus sequence, Calc 1 through Calc 3. So this is a more moderate substitution method problem. This one is actually a moderate to difficult substitution rule problem. Now this one looks pretty similar to this one, right? Here we basically have square root of x times square root of x squared plus number. Here we basically have square root of x times square root of x plus number, essentially. The main difference is I don't have a square on that x under the radical. If I had a square there, I know that u equals x squared minus 1. du is 2x dx. Again, this factor of 2 can easily be fixed, but this x dx is the main thing that I see that I've got here. This is just going to turn into something like integral square root of u du, more or less, right? We'll need a 1/2 here, but I know that I can solve an integral like that. But the difficulty is that I don't have square root of x squared minus 1. I wish there was like a button that you could just undo like the last 10 steps, but I don't have square root of x squared minus 1. I just have square root of x minus 1. Well, it's still the square root that's making things difficult, right? Let's just say, for instance, that instead of this, if I had square root of x times x minus 1 squared dx, this might be a bit of a pain to do, a bit of an algebra hassle, but I just multiply out x minus 1 squared, multiply x against all those terms, and then integrate term by term. Like I could do this just fine. This is easy. It might be tedious, but it's easy, right? It's not theoretically complex. It's not difficult. I can easily see the strategy to get through this problem. So it's really the fact that I have the square root of x minus 1. And in particular, if I had, say, like, x plus 3 squared square root of x dx, this is actually just as easy as the last one I wrote down. Maybe I end up with, whatever it is, square root x squared plus 6x plus 9 square root of x dx. This might look bad, but remember, square root of x is just x to the 1/2 power. It just combines with the others, right? I just get x to the 5/2 plus 6x to the 3/2 plus 9x to the 1/2 dx. And I mean, again, algebraically tedious, but I can see the strategy. I can see the path forward. No problem there. So I actually see that if instead of square root of x minus 1, if I just had square root of x, say multiplied by x, that actually would work pretty nicely. That would be a pretty conceptually easy problem. So maybe I still try to simplify this stuff under the radical. Maybe I just pick u equals x minus 1. I have a little bit of a problem here. Du then is just 1 dx. So I have basically 3 pieces under this integral. Integral of x times square root of x minus 1 dx. So I have my x piece out in front here, times square root of x minus 1 is square root of u, dx is du. I've used pieces 2 and 3, but I have not used piece 1. I haven't used this factor of x. I want to be really careful because this is a pretty easy mistake to make. I say, okay, I have square root of x minus 1 turns into square root of u, dx turns into du. I might accidentally leave off that x, right? If I'm looking kind of the other direction, like where does u fit in, where does du fit in, I might forget about that factor of x in front. So what do I do about that factor of x? Well, here I am going to note that x is u plus 1. Or I suppose if I really wanted to, I could write x as x minus 1 plus 1. That's certainly another way to write x inside the integral. And then x minus 1 I can substitute in as u. So if you really want to stick rigidly to that only working inside the integral so you don't make a mistake with your u's and du's, you could do that here. Or you could kind of work with your u and du substitution directly and see that x is u plus 1. Again, this is more like a, somewhere between moderate and challenging problems. So this is one that when you're doing it on your own, you're probably going to have a little experience with substitution rule already. It's not going to be one of the first few that you do. So at this point, you might be a little more comfortable just manipulating the u's and the du's more directly. Or if you wanted to manipulate things inside of the integral to get everything into the correct form, you could do that also. Right, so I see an x here, I want an x minus 1, I make an x minus 1, and then I fix it by adding 1. So I subtracted 1, I got to add 1 now. Not undo it. Give me u plus 1. Well, this is integral of u plus 1 times u to the 1/2. That's u to the 3/2 plus u to the 1/2. Integrating that du. This is u to the 5/2, which I apparently cannot write the number 2. There we go. And divided by 5/2 or times 2/5. U to the 3/2 divided by 3/2 or times 2/3 plus c. And again, it's kind of good form to put my answer back in the variable that it was originally asked in, the variable x. So I'm going to write this as 2/5 x minus 1, the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. Any questions so far? Okay, so like I said, this last problem maybe on the more challenging end of things. But we see that, we still can solve it with substitution rule. Okay, we also have a substitution rule for definite integrals, and that is if g prime is continuous on the interval ab, and if f is continuous on the range of u equals g of x, then the definite integral, integral a to b, f of g of x, g prime of x dx, equals the definite integral of f of u du, where the bounds are now going from g of a to g of b. So let's take a look at this in the context of an example. So example, integral 0 to 1 of sinh of 4x dx. So this is a pretty easy substitution to make. U equals 4x. This is one that we could definitely do by just kind of guessing and checking. But just going through the mechanics here. So du equals 4 dx. Now, when I write integrals like this, when I know that I've got different variables at play, I've got x in some places and u in other places, I want to be very explicit about everything. So I'm going to write integral x equals 0 to x equals 1. Typically, I'll only write one of the x's. I'll write like integral x equals 0 in the bottom and then just 1 on the top, but I'll be even more explicit now. And then we have sinh of 4x dx. I know that I want du to be 4 dx. I'll put in a 4 and take out a 4. Now I see that this is 1/4 integral f of u du, or sinh of u, right? Sinh of 4x is sinh of u, and 4dx is du. And I have to be very careful here, right? Very tempting to write integral 0 to 1, but this is integral from u equals something to u equals something else. When x is 0, u is 4 times 0. It is 0. So we actually are integrating from u equals 0, but when x is 1, u equals 4 times 1, or 4. So x goes from 0 to 1, but since u is 4x, u is kind of stretching things out by a factor of 4, u goes from 0 to 4. And now I can do this integral. This is 1/4. The integral of sinh of u is cosh of u, going from u equals 0 to 4. Or this is 1/4 cosh of 4 minus cosh of 0, or this is 1, so 1/4 cosh of 4 minus 1. So it is very easy to forget to change the bounds. So one thing you can do is you can take this approach. Now, personally, I like a different approach. I think this is a matter of taste and style, but I also think that there's a good reason for what I'm going to recommend. Going from this step to this step, there's an awful lot going on here. We're changing our integrand from the x's to the u's. We're making sure that we can write dx in terms of du. We're making sure that we've used everything in the original integral and nothing that's not in the original integral. We're doing all of this stuff with the u substitution. And now we've got one more thing to do in this same step. Change the bounds. So what would be a different approach here? Well, maybe I'll just copy this down. Is there a different approach that can split up the work? Can we make it so that there's not so much complexity in a single step? Well, I know that integral 0 to 1 sinh of 4x dx is just f of 1 minus f of 0 for some antiderivative f, right? So what can I do? I can come over here and find an antiderivative f. I want to find the antiderivative of sinh of 4x. Well, here I can do substitution. U equals 4x. Du is 4 dx. So I have 1/4 integral of 4 sinh 4x dx. My sinh of 4x turns into sinh of u. My 4 dx turns into du. This is 1/4 cosh of u. I only need an antiderivative, so I'll just let the c be equal to 0. So 1/4 cosh of u. But remember, I want to phrase it back in the original variable. So this is 1/4 cosh of 4x. This is an antiderivative of sinh of 4x. And now I can pop back over here. And I can say, well, this is 1/4 cosh of 4 times 1 minus 1/4 cosh of 4 times 0, or it's 1/4 times cosh of 4 minus cosh of 0, or minus 1. What I've done is effectively take this one huge step where I have to remember all of my u and du stuff and also remember to change my bounds. It's really easy, I find, at least for my way of thinking, like when I'm dealing with all of the u's and du's and the integrands and making sure I didn't miss anything there, it's really easy for me to get lazy and just write integral 0 to 1 down here and forget to change my bounds of integration. Personally, I like doing it this way because I have all my u and du stuff here. That's half the complexity. And then I'm switching my u back into x and evaluating. That's the other half of the complexity. And furthermore, I didn't ever have to change my x bounds into my u bounds. I changed my u in my function back into my x. I like this way a lot better, right? But you can, in theory, do it all in one step. This is definitely a little more writing. It's definitely a little more, a little more time spent just jotting things down. But I think in terms of the decrease in complexity, just being able to split the most complex step into 2 completely different steps, maybe even 3 different steps if you consider this to be an important step. In my mind, that's well worth it. So if I have to solve a definite integral where I'm going to use substitution rule, I'm probably going to, unless it's a really simple one, like this one's not that bad, so I probably would just, but I wouldn't use substitution for this anyway. This would be a guess and check problem. Unless it was a really simple one, I would bump off to the side, do some scratch work, find an antiderivative, come back, and then plug in. So that's my preference, but you really can do it either way. But I would be a little hesitant to use the theorem just for the practical reason that it lumps so much into a single step. You need to check like every single thing that you write down and make sure that it corresponds correctly. There's already a lot of stuff you're checking the bounds. It's really easy to just forget and get lazy and just copy the bounds down along with the integral sign, right? Like it's really easy to just write integral 0 to 1 and then start checking. In my mind, a lot of times like the bounds almost are like tied in with the notation for the integral sign, so I'm even less likely to be super careful about the bounds. So this is what I find works well for me, and makes me make fewer errors. So less error prone is always a good thing. Okay, so I want to, let me get these spaces out of here. I want to take a couple minutes here and go through some substitution rule practice. So we've got about 40 minutes left in class, so we actually have a pretty decent amount of time. And I would like to run this a little bit like a practice session or a review session. I know that we kind of only introduced substitution rule today, but I think actually going through and struggling with it a little bit for a couple of these problems is actually kind of useful. So I think what we'll do is we'll take, I've got all 5 problems kind of on the screen here. We'll introduce problem 1. I'll give you maybe 3 or 4 minutes to work through this one. We'll come back, we'll work through this one as a class. Then we'll take, 3 or 4 minutes for problem 2 and go down the line. So I think that'll use up most of the rest of our time, but it'll also give you a chance to practice some of this, watching me do a bunch of substitution rules when you're like, wait, how did you choose that u? That's a lot less instructive than you actually choosing a couple of u's. Maybe it works right away, maybe it doesn't work, you have to back up a little bit, or maybe you don't get it at all, and then but you've tried it a couple of times and then you see why my way works and maybe your way didn't. Or maybe you see that you used a slightly different u than I did, and in some instances there are a few different u's that can actually work and get you the right solution. So take a look starting at problem 1. If you finish up before we come back and come back together to work through the solution. You can start working on part two or down the line, but start on problem one. We'll come back and maybe about 3 minutes for this one. This should be a shorter one. So we'll come back in about 3 minutes, work through the answer, and continue on. Okay, let's work through this one. It's about 2.5 minutes, but I think this is a pretty straightforward one. So here we have 3x minus 1 squared dx. We could, of course, expand this out just algebraically. Factoring would be difficult then, though. We probably could make an educated guess here and get the answer that way, but we're just practicing using substitution rule here. So I think probably the best u to choose is 3x minus 1. Du would then be 3 dx. And we don't have a factor of 3, so we can kind of put it in and take it out, multiplying by a 3/3 inside the integral, pulling the 1/3 factor out of the integral. And this ends up being 1/3 integral of u squared, that's this bit, du. I've used everything in my previous integral and nothing that's not in it. So it looks good. All of my accounting, my bookkeeping works out. So this is 1/3, and this is going to be u cubed over 3. So it's another 1/3 u cubed plus c. I can make this a 1/9. U cubed is going to be 3x minus 1 cubed plus c. I think that's right. I can differentiate. I get 3 stuff to the second. One of the powers of 3 cancel, so I get 1/3 times the derivative of the inside, which is another factor of 3. Another factor of 3 will cancel, and I get 3x minus 1 squared, which is exactly what I'm looking for. Okay, so take a look at problem 2 now. Maybe we'll do about, let's say 3.5 minutes for this one. I think that should work well. So 3.5 minutes, we'll come back and chat about it. Okay, so let's take a look at this one. So I think probably the initial thought here is we'd want to use u equals square root of x. We might be a little hesitant because we might think that we're going to get something like integral of e to the u over u. Just at a glance, it looks like, is this going to turn into e to the u over u du? Might be a little hesitant because of that. I don't know how to integrate this. However, if we, take another step further, we note that if u is root x, du is 1 over 2 root x dx. So actually this root x is going to combine with that dx, and that's going to be part of du. So it actually does work out okay. Especially with square root of x, there's a lot of things like this that look very strange. And because basically the derivative of square root of x is like 1 over itself, more or less, um, a lot of things that look very strange kind of turn out okay, and also kind of a lot of things that look like they should turn out okay maybe don't turn out so great. So the square root of x can be a little bit of a tricky one, but we do see if we have u equals root x, du is 1 over 2 root x dx. So we can rewrite this as e to the root x times 1 over root x dx. We can pop a 2 on the bottom and multiply by 1 in the front as well. So that fixes the constant bit with du. So we see this 1 over 2 root x dx becomes du. E to the root x becomes e to the u. Our factor of 2 in front comes down. We've used everything in the integral, nothing not in the integral, so all of the bookkeeping works out nicely. And then, of course, just integrating e to the u du is just e to the u. Windows wants me to update, of course, in the middle of things. So we have 2 e to the u plus c, and then I plug my square root of x back in for u, 2 e to the root x plus c. As kind of a side note, if you had chosen u equals e to the root x, maybe you got a little greedy with u and tried to put a bunch in there. What's du? Well, e to the stuff differentiates to e to the stuff times the derivative of stuff. What's the derivative of root x? Well, it's 1 over 2 root x dx. Well, hey, that's like almost exactly, I'm trying to get them both on the screen here. Oops, went a little too far. Hey, that's almost exactly what we have inside of our integral. Right, so we could take an approach a little more like this. We would be integrating, let me just copy that over here. So integral e to the root x over root x dx. If we took an approach like this, where u is e to the root x, what does our integral actually turn into? Well, we can put a 2 and a 1/2. That's not hard to fix. We actually get twice integral. This whole stuff inside the integral, be careful. The stuff isn't u. The stuff is all du inside the integral, right? Or this is just like the integral of 1 du, basically. What is this? Well, this is just 2u plus c, or 2e to the root x plus c. This actually worked out so nicely, it might even be confusing because we're like, okay, how do I do this integral? Well, this is actually such a simple integral to do. It's just like integral of 1 du. It just integrates to u. So if we got a little bit greedy, in this case, it works out okay. So we could really get away with doing it either way. I would say the in blue is probably the slightly more natural way to do it, but if you put a little extra in there, like u equals e to the root x, trying to get rid of this numerator, which is also, kind of causing some complications, that way works as well. Couple paths to the answer for this one. Okay, let's look at part 3 here. Problem 3. Take maybe about 2.5 minutes for this one. I will give you a hint. There's no like real big fancy trig identity kind of stuff here. You don't have to do anything super crazy. It really is mainly a substitution method problem. So don't go too far down any trig rabbit holes. Okay, so let's take a look at this one. I think probably our first intuition is to make this integral tan x dx, which I think is a good intuition. We note that that's not helpful though. We need to be really careful here. The integral of tangent of x dx, I'm looking for a function whose derivative is tangent x. Now I know the derivative of tangent x is secant squared x. That's a nice thing to know, but it doesn't help me here. So I don't want to write, integral tan x dx equals secant squared x. That's in some loose sense going the wrong direction. We're looking for a function whose derivative is tan x, and I think most of us don't know off the top of our head what function that would be. I know that I certainly don't. So I don't remember that this is something like our answer down here. But I do notice that cosine and sine are, roughly speaking, each other's derivatives. So that means if I use one as u, the other one can basically be du. And I note that sine x over cos x is kind of like 1 over cos x times sine x dx. Or if I pick u to be cos x, then du looks more or less like what I have left over, right? It looks like negative sine x dx. So this is the integral of 1 over u, and then, well, du would be negative sine x dx, so sine x dx is negative du. So negative integral 1 over u du, that integrates to negative log absolute u plus c, or negative log absolute cos x plus c. Right. So if you started going this route, that's probably where most people's intuition would lead them. And I think that's actually good intuition. Look for something simple first, but that doesn't really yield anything. Okay, we went that route, didn't get anything. Is there another route we could go? Yeah, look for a substitution and note that sine and cosine are each other's derivatives, more or less. That's going to be really helpful for a substitution. Okay, let's look at problems 4 and 5. And that will probably take us to the end of class time. So we'll do, let's do about 4 minutes for problem 4. I think that should be good. And then a little longer than that for problem 5. Okay, so for this one, let's take a look at it. I think this is a fairly straightforward one, but we do again have the choice. We can either use the substitution rule for definite integrals and make all of the changes in one step, or we can kind of split it into two parts. I think we'll do the one step method here, and maybe I'll plan to do the two parts method for number 5, just so you can see both of them again. And of course, strategically picking the everything at once method for the simpler of the problems, so that hopefully that keeps me from making any mistakes. So here I want to do something like u equals x squared. I think that's going to work pretty nicely. That's going to give me a sine of u, and then du is going to be 2x dx, and nicely enough, I have an x dx that'll work pretty nicely for du. I'm going to choose to rewrite this integral, being explicit about my bounds, integral x equals 0 to 1. And I'm going to write this as 2x sine x squared dx. I put a factor of 2 in. I need to take it out, so I need a 1/2 there. Or this is going to be 1/2 integral. Now, when x equals 0, u, which is x squared, is also 0. So u goes from 0. When x is 1, nicely enough, 1 squared is 1. So u goes from 0 to 1 as well. Sine of x squared is sine u. And then my 2x dx is du. So I've got my constant in front, my 2x dx turned into u, my sine x squared turned into sine u. Everything in my integrand is taken care of, and I haven't used anything extra that's not there. And I switch my bounds appropriately into u. Even though they turn out to be the same number, I did make sure that I did that step. So this is 1/2. Now I integrate sine u to negative cos u from 0 to 1. Or this is negative 1/2 cos 1 minus cos 0. Or I suppose this is what, maybe 1/2 times 1 minus cos 1 maybe is the nicer way to write this, something like that. Okay, and then let's go to problem 5. Yeah, definitely the most challenging one of the group here. If you need to look back at your notes, there was one we did that was similar to this one. Take a look at this one and maybe take about 5 or 6 minutes for this one. So we'll come back in 5 or 6 minutes, and I'll write up a hint in maybe 2 or 3 minutes. Okay, so let's work through this one. So the one we have here is similar to our pretty challenging one from earlier. We have this difficulty with the square root. We want to simplify the square root, but we don't have a nice du, so to speak, outside of here. Or really, we have more complicated stuff than we end up with in du. So if I pick u to be x plus 1, I have a du as dx, and I don't really know initially what to do with this extra x that's out here. It's easy if I'm not being careful to forget about that extra x and just not write it in the next line down and write something like integral of square root of u to u and have the wrong answer. So but I do note that that x looks like u minus 1. So I can write that x in terms of u. And I'll use that same substitution over here. I'll choose to come over here, get an indefinite integral, get that as a function of x, come back, evaluate that at x equals 1, minus that evaluated x equals 0, and that gives me my answer. So I end up with in my indefinite integral, the x turns into u minus 1, the root x plus 1 turns into a root u, and the dx turns into du, right? Du ended up just being dx here. Really all we did is we kind of, smushed that complexity with the x plus 1 into complexity that's outside the square root. We almost squished the square root insides down, and that popped that into the other factor outside of the square root, but I'd rather have the complexity outside of the square root than inside of it. So that's really kind of what we did here. We multiply this out. U times u to the 1/2 gives me u to the 3/2 minus u to the 1/2 du. And then we integrate this, add 1 to the power, divide by the new power. Just be careful when you're adding that you kind of get all your fraction stuff right. So 3/2 plus 1 is 5/2. And then we're dividing by 5/2 or multiplying by 2/5. And similar for minus 2/3 u to the 3/2. We put our x back in, u is x plus 1. So it's not the prettiest function to evaluate, right? A little more algebra, a little more writing things down to avoid that extra hassle in converting x to u and doing all of that in one step, right? I already was doing a lot in this step here. And I would have had to do an extra piece where I have to convert x equals 0 to u equals 1 and x equals 1 to u equals 2. Easy to forget to do that. Again, it's not the end of the world. It's not like it's so much more difficult to do or anything like that. But when you're doing a lot already, it's easy to make a silly mistake like that. So evaluating big F of x over here at x equals 1, well, x plus 1 then is 2. So this is 2/5, 2 to the 5/2 minus 2/3, 2 to the 3/2. Then subtract off that evaluated x equals 0. This 1 to the 5/2 and 1 to the 3/2 just goes away, and I get 2/5 minus 2/3. And whatever this turns out to be, we might be able to simplify this a little bit, but it's not going to simplify to anything super nice. Okay, any questions on substitution rule or any of the administrative stuff that we talked about earlier? All right, let me stop the recording.